Kepler's laws can be derived with those simple equations I said before. So let's go ahead and talk about them. Kepler's laws, Kepler actually came up with these laws before Newton knew what was going on, but Newton used this information to figure out his laws, or to verify them. But let's take a look at Kepler's first law. Kepler's first law is that all the planets orbit in ellipses. It was thought that because creation must be perfect, that they all must orbit in circles. And Kepler realized when he was watching these planets for years after years after years, sometimes they went slower, sometimes they went faster. And he figured out that it must be because they orbit in ellipses, not in circles, although a circle is an allowed orbit. A circle is an ellipse, and the inner planets actually have pretty close to circular orbits because a circle is an allowed orbit. It is an ellipse. Let's take a look at the anatomy of an ellipse here. This is important. An ellipse has three main measurements. This whole thing right here, this long distance right there, is called the major axis because it's the longest axis of this ellipse. Now, half of that, this is called the semi-major axis. And we use the symbol A to represent the length of that. The semi-major axis, it is half of the length of the major axis. That's A. We also have the minor axis, which is this. And as you guessed it, when we find half of that thing, we get the semi-minor axis, which is this. And we call that B, the semi-minor axis. And then we also have this thing called C, which is the distance from the center to the focus. I don't even know if there's a specific name for this, but this is the distance from the center to the focus of the ellipse. When you take any point on the ellipse, so let's take an arbitrary point right there, the distance from this focus to that point plus the distance from that point to the other focus, the sum of those is a constant for every point on this. We can do that with a physical derivation with a string and two push pins. So that's pretty cool. Mathematically, you can find out that this right here is true. A squared is equal to B squared plus C squared. In other words, the semi-major axis squared will equal the sum of the semi-minor axis squared plus this center to focus distance C squared. That distance is A. This is B and this is C, just like Pythagorean theorem. That is Kepler's first law, simply that the planets are all in elliptical orbits with the sun at one focus. The sun is right here. There's our sun. It's at one focus of the ellipse. And you don't need anything at the other focus. The planets will just go around the sun. That's Kepler's first law, simply that the planets orbit in elliptical orbits with the sun at one focus. Let's take a look at Kepler's second law. The second law is that planets sweep out equal areas in equal times. So what the heck does that mean? So let's take a look at a planet at a couple different points in an orbit here. So here it is at one spot right there. There's our planet. And it's going around the sun here. Here's its path like that. And this all happens in some time delta t. Now, if you figure out all the area in here, this area right in there, that's what we call the area that's been swept out. In other words, if our planet goes from this spot from right there to right here, we draw the arc and then the lines from the sun there, and this area is the area swept out in a time delta t. In the same time delta t, at some later time though, same delta t as before, it will sweep out the same area. That area will be the same amount. That's what Kepler was saying by the fact that the planets sweep out equal areas in equal times. And what this tells us is that the speed of the planet has to change. Look at this and you tell me, where is the speed of the planet faster? Over here are over here. For those two areas to be equal, the speed of the planet has to be greater over here. Closest spot to the sun we call perihelion. Per means near, and it kind of sounds like it. Perihelion, near helion, the sun. This is the aphelion, the farthest point away, and you can use the mnemonic A is for away, aphelion is right there, the farthest point from the sun. It actually moves fastest when it's closest to the sun. And we can prove this, and we will, using conservation of angular momentum for a particle. Remember, angular momentum for a particle is r cross p, its momentum, and that is going to be constant for any planet going around the sun, as we will show. If we have a planet anywhere on this thing, here's our planet, the force exerted by the sun is pointing this way. There's the force right there. But the r, the displacement from the axis of rotation to point of force application, is back this way. So there's r. Those are 180 degrees apart. So, or the angle between the r vector and the f vector are 180 degrees. So the cosine of 180 is 0. So r cross f is 0. There is no torque exerted by the sun on any of the planets because it is a central force. Notice that we have F and R are collinear. It may not look like it perfectly there, but those are along the same line. So the sun exerts no torque on any of the planets, so angular momentum is conserved. And that's how we're going to derive the speeds at perihelion and aphelion. Let's go on to Kepler's third law. Now, Kepler's third law we are going to derive, again, using those equations that we started with at the beginning of the lecture. But Kepler's third law, in brief, is that the period squared of a planet's orbit is proportional to the average radius or average distance from center to center cubed. Our average is actually A, the semi-major axis. So that is something we're going to need for both AP Physics C and AP Physics 1. That is the average distance from the satellite to the orbited body. For circular orbits, it's exactly just the radius, and a circular orbit is an allowed orbit. So what we're going to do is we're going to derive this relationship, Kepler's third law, for circular orbits using the simple relationship that what is providing our centripetal force in this situation? The force of gravity is providing it. So again, the centripetal force is not some kind of separate force. You always got to figure out what's providing it. And when you calculate the net centripetal force, it will always be equal to mv squared over r. What's providing it in this situation right here? We have a sun and a planet of mass m. Well, the universal gravitational force is providing it. Now, why can't we use mg for this? We don't know what little g is way out here far from the sun. We're not talking about g on Earth. We're talking about little g due to the sun. We don't know what that is. How much acceleration, if the Earth suddenly disappeared, how quickly would we accelerate towards the sun? We don't know that. You'd have to do a calculation to figure that out, which we will do, but we don't know that at this point. So we can't use m times little g. We have to use big G, m, or mass of the sun, mass of the planet, over the center-to-center distance of those two. Squared. So as we'll find out, the mass of the satellite, in this case a planet, does not matter. So notice that m cancels m right here. It doesn't matter what the mass of the satellite is. If you put a grapefruit right out there, it would orbit the sun at the same speed as the Earth. Or if you put Jupiter right there, it would orbit the sun at the same speed. The mass of the satellite for circular orbits doesn't matter. Now that is a slight approximation. It does assume that the mass of the sun or orbited body is much, much greater than the mass of the planet, but that works great for us because the mass of our sun is so much greater than the mass of any planets. And we are going to right now, let's go ahead and derive this thing right here. We are going to derive that right now. We've got a sun of mass big M, capital M, and we have a small planet of mass little m. This distance is r. The center to center distance r away. So let's go ahead and derive Kepler's third law. So we're going to start off with the net force centripetal equals mv squared over r. And make sure that you understand what this little m is. That's the mass of the planet, because that's the object going around in a circular orbit. Now, what is providing this Fc? Well, it's the force of gravity. But we have to use the universal gravitational force. Fg is providing this net centripetal force. We have to use Newton's universal law, so that'll be big G, big M, little m. It's the mass of the sun, mass of the Earth or planet, over r squared, is providing the centripetal force, mv squared over r. Now, you don't see the period in here, the period of motion, capital T. We've got to get that in there somehow. How do we do that? It's easy. Note that the speed of the orbit is equal to 2 pi r. That is the distance around one. So how long does it take to do that? It takes the period t to get around there. Period we'll measure in seconds. So, and what is that for the Earth, by the way? What is that period of orbit for the Earth? Think about that. If you understand what the period of orbit is, then you know that that is 1 year, 365.25 days. So there's our speed. So that's what we can substitute in there for that. So let's go ahead and do that. So we get G, so this will lead to this. Big G, big M, little m over r squared equals m times what we just found out, 2 pi r over the period, right there. We got to square that over r squared, or over r. Okay. So now let's just do some cancellations here. We can get rid of the mass of the planet. The mass of the planet does not matter. And we'll do, let's go ahead and multiply through here so we can do some more cancellations. Big G, big M over r squared equals, when I do this, I get 4 pi squared, because I just squared 2 pi. We get r squared. And then we get, on the bottom here, this is r times t squared. So I'm going to do some cancellations. This cancels that. So that goes away. And then I'm going to just move things around a little bit here. So I'm going to actually take this t and put it over there, t squared. And I'm going to take these two r's, this r squared right here. I'm going to put this over there. So that gives us something times r cubed. We're almost there. And what is the factor when I do all the math? You get 4 pi squared stays on the top over there, over big G and the mass of the sun. So you can see we have just derived it for circular orbits. The period squared of the planet's orbit will equal this constant, which depends on the mass of the sun. That's a capital M right there. 4 pi squared over G big M times r cubed. So t squared, the period squared, is proportional to r cubed. That is Kepler's third law. But keep in mind, how we derive this all started from just this. And this is the main thing you have to understand, is right here. This thing is what you need to get. The force of universal gravitation is what is providing that centripetal force. This is the key step right here that you have to be able to do, and you will have to be able to do this for several problems. This equation right here, equating the force of gravity and the centripetal force, will solve a whole chunk of these problems. If you realize, okay, the centripetal force is being provided by gravity, I would say a good, maybe a quarter to a third even of all these problems can be derived using, can be solved using this relationship right here.